This is Kevin Cole at the University of Nebraska. The topic is thermodynamics, and the example is kinetic energy of an automobile. What energy is contained in a 2,000-pound car traveling at 50 miles an hour or 75 miles an hour? And where does that energy go when you stop the car? Well, here's the theory. The kinetic energy is 1/2 mass times velocity squared. And I want to think about a process from state 1 to state 2. State 1 is a car traveling at velocity v1, and state 2, the car is stopped. Velocity is 0. When we compute a process, we always go final minus initial. So I've got 1/2 m v2 squared minus v1 squared, and v2 is 0. So I'm going to get a negative kinetic energy. So kinetic energy goes down when we're stopping. Let's say that our car is 2,000 pounds, and that's the same as 907 kilograms. I want to make a little table here. I want to compute the speed in meters per second, and then I want to compute the kinetic energy. I need a conversion for speed, so let me do that up here. Let's convert 1 mile per hour by multiplying by some constants. There's 5,280 feet per mile, and then I want to get meters. There's 0.3048 meters per foot, and there's 1 hour is the same as 3,600 seconds. So if I compute those guys, I'm going to get 0.447 meters per second. 0.447 meters per second, the same as a mile per hour. So that's the conversion factor I'm going to use down here. So let me take my 50 miles per hour and multiply it by 0.447, and that'll give me 22.35, excuse me, 22.35 meters per second. All right, let's compute 1/2 mv squared. See what that looks like. My mass is 907 kilograms, and my velocity for the low speed case is 22.35 squared. What are the units on that? Let's look at that for a minute. Units are going to be kilograms times meters squared per second squared. Well, what is that? Well, this has the same units as, let me reorganize it this way. Let me write kilograms times meter divided by second squared, and all of that times meter. That's the same, but this guy here is a Newton. We can recognize that from Newton's second law, F equals ma. And then I have left newtons times meters, which is the same as a joule. Okay. So that's the units I'm going to get here. When I crunch this number, this is going to give me 1/2 times 907 times 22.35 squared is 226,500, and the units is joules. And I can do the same thing for the 75 mile an hour problem. Let me take 0.447 times 75 is going to give me 33.53 meters per second. And when I square that, multiply by mass, and multiply by 1/2, I'm going to get 510,000 joules. All right, so that's the energy change. Before I finish with this part, though, let's think about how much the velocity changed. When I went from a velocity of 50 miles per hour, 75 miles per hour, the velocity goes up by 50%. How do we compute that? That's the new value minus the old value divided by the old value times 100%. And that's 25 over 50 is 1/2 times 100% is 50%. What about the kinetic energy? The kinetic energy goes up by, well, let's compute it. I've got 510 kilojoules minus 226.5 kilojoules, that's the old value, divided by the old value, 220, I didn't get that right, 226, well, can I erase that? 226.5 divided by 226.5 times 100%, that's a change of 125%, much larger, much greater. This is because the kinetic energy goes by the square of the velocity. All right, so here's the energy that's lost for these two velocities. Where does that energy go? It goes to the brakes and it heats them up. Suppose we've got disc brakes, and suppose all the discs together weigh 10 kilograms. How can we analyze that? Well, the first law says that heat minus work equals a change in internal energy, and a change in internal energy for solids is mass times specific heat times temperature change. Let's compute the temperature change. That it's going to be converted to heat, so we've got Q. What's the work? Well, for a brake disc that's not changing its size, it's 0. So let's combine these two ideas together, and we're going to have Q equals the change in internal energy, which is equal to mass times specific heat times delta T, and I'm going to solve for delta T. Delta T is going to be Q divided by mass divided by specific heat. Let's put some numbers in. Our Q, well, we've got the iron brake disc is 0.45 kilojoules per kilogram per Kelvin. Let's use the 75 mile an hour value. Let's use this value here. So I'm going to put in 510 kilojoules divided by 10 kilogram brake discs divided by 0.45 kilojoules per kilogram per Kelvin. And I've got some units going to drop out here. My kilograms are going to drop out, and my kilojoules are going to drop out, and that's going to leave me with 113 Kelvin. That's my change in temperature. The temperature goes up. Now, that's a pretty big temperature, but that's okay. If the brakes can cool between stops or between applications. On the other hand, though, if you are descending a mountain, now we don't have any mountains in Nebraska, but we travel to them, you need to either pump the brakes and not apply them continuously, and use low gear to save the brakes. If the brakes get too hot, they will fade and you won't be able to stop. All right, let's recap. Scrolling back up here, we're looking at the kinetic energy of an automobile, and we looked at a process from state 1 to state 2. When we computed that, we did final minus initial, so in this case the kinetic energy was negative for stopping. We found the kinetic energy for two speeds. We computed a change by dividing by the old value when we computed a percent change. When we computed where that energy went, it went to heat. We solved for the temperature change, and we used, we had units in kilojoules, so I had to put down my value of the energy in kilojoules so it wasn't off by a factor of 1,000. And if you descend a mountain, be sure to save your brakes. Then all will be well.